Hi everybody. So watch this video after you watch the other one. Okay, so this is coming up with a formula for path difference. Last year you didn't have anything mathematical to do with two-slit interference. This year we're just going one step more. Okay, so I'll just explain what this diagram is. So this one here just shows the two slits, S1 and S2, and this is a screen where you get the interference pattern. So N0 is your central antinodal line, and let's say that's your first antinodal line. So we're going to come up with the formula. Now I'll just explain what some of the things are. The distance from one slit to the other is d, small d. Capital L is the distance from wherever your slits are to the screen, and x is the distance from, it's called the fringe spacing, so it's the distance from your central antinodal line to the first one. Okay, now the red line actually shows these are the waves going from S1 to P, and this other red line are the waves going from S2 to P, and they meet there. Okay, now if you can easily see from this diagram that the distance from S2 to P is greater than S1 to P. S1's closer. So this difference in distance, this little gap here, is what's called path difference. So we're going to just look at this triangle for now, which I've drawn over here. Okay, so D is the distance of this gap, and this is your right angle. Okay, so that these two are equal, what's left of it. So that's your angle theta. So if you look at this right angle triangle, D is actually the hypotenuse, this is the opposite. So you get sine theta is PD over D. Okay, or PD, path difference, is D sine theta. Now we know for any antinodal line, path difference is n lambda. So you come up with the formula n lambda equals D sine theta for an antinodal line, or n minus half lambda is D sine theta. So what does n stand for? N is the order number, lambda is the wavelength of the wave, d is the distance between the slits, and theta is the angle that the central antinodal line makes with that line. So this green triangle is just averaging it out. Okay, so that's the formula that you use to solve problems. But now there is also what we call one more formula, which you can use for two slits. So what I've drawn on the next page is just the green triangle. Okay, so this one, just done it in green. So just look at the green triangle. So this is when L is very large compared to X. Okay, so this theta, your sine theta, is actually opposite over hypotenuse. But if X is really small and L is very large, your sine theta becomes nearly equal to tan theta. So tan theta is opposite over adjacent. So this n lambda over d sine theta can be written as n lambda is equal to d, and instead of sine theta we can write x over L. So this formula n lambda equals dx over L can be used to solve problems so long as it is only problems for two slit interference. Okay, that is where X, the fringes are very, very close together, and L is very large. At this point in time, you don't know of any other sort of interference patterns, but in the next lesson after the weekend, we will be learning about multiple slit interference where you cannot use this formula, you can only use the one with the sine theta. Okay, so that's that formula. And there's one more thing, which is I'm just going to tell you how to answer some explanation questions based on these formulae. So suppose you have red light and green light, and use that with two slits, and they're going to ask you, like, what can you say about the fringe spacing, or how far apart are the fringes? So the thing is, red light has a longer wavelength compared to green light. Okay, so the pattern that you see is for red light, the fringes are far apart, and for green light, they're close together. How do you justify this? You just use the formula n lambda equals d sine theta. When wavelength increases, theta sine theta will increase. So theta increases, so sine theta increases, and that is why you will have, so the light is diffracted by larger angles. Okay, so it's all to do with diffraction. And the other thing is, what happens if you bring the screen closer? So this is just how, the light travels to form the fringes. If the screen is far away, that means if L is very long, you can see that the fringes are far apart. But if you bring the screen really close, then the fringes are close together. So you can justify that by using the second formula. And lambda is dx over L. If L increases, sorry, it's got rubbed off, x will have to decrease. Okay, so if L becomes bigger, that means the length it's further away. Okay, then, sorry, x will have to increase as well. So they'll both increase. If L increases, x will have to increase to keep n lambda the same. Okay, so that's the answer to these. And that's all for now. I hope this lesson made sense. And what you have to do is, there are some problems on two-slit interference. I posted the question sheet as well, but just do the questions on two-slit interference. I put the answers up as there as well for you. Okay, bye for now.